In 1969, we landed humans on the moon using computers weaker than your microwave. Today, with smartphones containing more processing power than every Apollo mission combined, returning to that same lunar surface has become one of the most complex engineering challenges humanity has ever attempted. This is not a failure of technology. It is something far stranger. We dismantled the factories. We retired the engineers. We lost the blueprints. The rockets that carried astronauts to the moon no longer exist, and rebuilding them is not simply difficult, it is impossible. The knowledge itself has vanished. What remains is a paradox that reveals uncomfortable truths about how civilization actually works. We are not less capable than our grandparents. We are trapped by constraints they never faced. If you are ready to discover why going backward in space is harder than going forward, why safety can become a barrier, and why the greatest engineering achievement of the 20th century became almost impossible to repeat, hit that like button and subscribe. You're about to see the moon landing in a way nobody has explained before. Settle in and make yourself comfortable. Let's begin. Picture a factory the size of 40 football fields. Inside this cavernous structure, more than 10,000 workers assemble the most powerful machine humanity has ever built. Specialized welding equipment joins aluminum alloy panels thinner than a credit card, but strong enough to withstand forces that would crush a nuclear submarine. Custom-built tools exist nowhere else on the planet. The engineers who design these tools are inventing solutions to problems nobody in history has ever encountered. Quality control inspectors examine every weld under magnification, rejecting components for flaws invisible to the naked eye. This factory produces exactly one product, the first stage of the Saturn V rocket, the vehicle that will carry human beings to the moon. Now picture that same factory 15 years later. The workers are gone. The specialized welding equipment has been sold for scrap metal or donated to museums, where school children press their faces against glass to see relics of a vanished age. The custom tools that existed nowhere else have been melted down for their raw materials. The engineers who understood how everything fit together have retired to Florida condominiums, moved to aerospace companies building commercial aircraft, or passed away with their knowledge unrecorded. The blueprints remain in filing cabinets and government archives, thousands upon thousands of technical drawings that document what was built. But the institutional knowledge, the countless small decisions, workarounds, improvisations, and tribal wisdom that made those blueprints actually function has evaporated like morning dew beneath a rising sun. This is not a hypothetical scenario constructed to make a dramatic point. This is precisely what happened to the Michoud assembly facility in New Orleans, Louisiana, where every Saturn V first stage was manufactured between 1961 and 1973. The story repeated itself with haunting similarity across every major component of the Apollo program. The command module factory in Downey, California, fell silent. The lunar module plant in Bethpage, New York, shifted to building other aircraft. The rocket engine test facilities in Hancock County, Mississippi, stood dormant for years. The guidance computer laboratories at MIT's Instrumentation Laboratory dispersed their teams to universities and private companies across the country. Throughout his tenure as NASA administrator, James Webb repeatedly warned Congress that terminating Apollo production capability would destroy industrial infrastructure that could never be rebuilt at comparable cost. The factories, the tooling, the trained workforce, the supplier relationships, all of these represented investments that would evaporate the moment production ceased. Webb urged legislators to consider maintaining at least minimal production capability to preserve options for future lunar missions. Congress ignored him. The political appetite for lunar exploration was already fading even before Neil Armstrong's boot touched lunar soil. Between 1972 and 1975, the entire industrial base that put human beings on the moon was systematically dismantled, not mothballed for potential future use. Not preserved in any meaningful sense, actively destroyed, piece by piece, contract by contract, as accountants calculated the savings from eliminating maintenance costs on idle facilities. The scale of this destruction defies casual comprehension. Consider just one component, the F-1 rocket engine, the most powerful single-chamber liquid-fueled rocket engine ever successfully flown. 5 of these engines powered each Saturn V first stage, producing a combined 7.5 million pounds of thrust at sea level. This thrust figure represented enough raw force to lift a fully loaded aircraft carrier straight off the ocean's surface and accelerate it toward the sky. Each F-1 engine stood 19 feet tall and measured 12 feet across its bell-shaped nozzle. The turbopumps that fed propellant to the combustion chamber moved liquid oxygen and kerosene at rates exceeding 40,000 gallons per minute. The F-1 was manufactured by the Rocketdyne division of North American Aviation at their facility in Canoga Park, California. Production techniques existed only within that specific facility, developed through years of trial and error as engineers solved problems that textbooks could not anticipate. When production ended in 1968, after building 65 flight-worthy engines, Rocketdyne retained the technical drawings and specifications. What they did not retain, what they could not retain, was the institutional knowledge embedded in the workers who actually built the engines. These workers understood thousands of small details that never appeared in any official documentation. They knew which welds required extra attention because the metal behaved unexpectedly at certain temperatures. They knew which dimensional tolerances could be pushed slightly, without affecting performance, and which tolerances were absolutely critical. They knew which suppliers' aluminum stock worked best for specific components, and which batches should be rejected despite meeting written specifications. They knew the subtle signs that indicated a part was about to fail inspection, and the equally subtle signs that a marginal part would actually perform flawlessly. This knowledge existed only in human memory, passed from experienced technicians to newer workers through years of side-by-side collaboration. None of this knowledge was recorded because nobody imagined it would ever be needed again. The Apollo program was not designed for repetition. It was designed for achievement, for reaching the moon before the Soviet Union, fulfilling President Kennedy's challenge, winning the space race. Once victory was achieved, the assumption was that future programs would build upon Apollo's lessons rather than replicate Apollo's hardware. New rockets would be designed using new technologies. The Saturn V would become a museum piece, its production methods relegated to historical curiosity. This assumption proved catastrophically wrong. Decades later, when NASA began exploring options for returning humans to deep space, engineers naturally looked to the Saturn V as a reference point. The rocket had worked magnificently, launching 13 missions without a single failure of its first or second stages. Surely the accumulated knowledge from this success could inform new designs. Surely the blueprints and specifications preserved in archives could shortcut development of new heavy-lift vehicles. What engineers discovered instead was deeply troubling. The existing documentation was incomplete in ways that prevented straightforward reconstruction. Critical manufacturing specifications had been recorded on supplementary documents that were subsequently lost when contractors cleaned out old file cabinets. Engineering change orders that modified original designs were not always incorporated into master drawings. Tribal knowledge about how to interpret ambiguous specifications had vanished with the workers who possessed it. Worse still, many components had been manufactured using techniques that no longer existed in any industrial context. The specific aluminum alloys used in certain structural components were no longer produced by any supplier. The companies that had made those alloys had been acquired, merged, dissolved, or shifted to different product lines. Reconstituting the alloy formulations would require metallurgical research that might take years. Even if engineers could specify exact material compositions, no existing facility possessed the equipment to produce them. The specialized tooling required to shape these materials had been scrapped. Factory floors that once held massive forming presses and precision welding fixtures now held completely different equipment for completely different products. Recreating the tooling would require reverse engineering from fragmentary documentation, a process potentially as expensive and time-consuming as the original development. The F1 engine presented particularly acute challenges. When NASA's Exploration Technology Development Program conducted a detailed study of the engine in 2013, engineers attempted to build a simplified version using advanced manufacturing techniques. They discovered that, even with modern computer-aided design tools, three-dimensional printing capabilities, and simulation software that would have seemed magical to 1960s engineers, certain aspects of the F1 design remained mysterious. The combustion chamber presented the most significant puzzle. Early F1 development had been plagued by combustion instability, violent pressure oscillations that could destroy an engine in milliseconds. Rocketdyne engineers solved this problem through extensive trial and error, testing modification after modification until they found configurations that worked reliably. The solutions they developed were empirical rather than theoretical. They knew what worked, but not fully why it worked. The knowledge was embedded in the hardware geometry rather than in equations that could be transferred to new designs. Modern engineers studying the F1 could see what the combustion chamber looked like. They could measure every dimension with precision far exceeding original manufacturing tolerances. What they could not determine was which dimensions were critical and which were incidental. The original engineers had tried many configurations before finding stable solutions. The final design incorporated features that prevented instability, but which specific features mattered most remained unclear. Some design elements might have been essential, others might have been artifacts of the development process, retained simply because no one had tested what would happen without them. Recreating the F1 engine would require either replicating the original design exactly, impossible because certain materials and processes no longer existed, or developing a new engine through similar trial and error processes. The second option would likely take years and cost billions of dollars. Modern simulation tools could reduce some testing requirements, but combustion dynamics at the extreme conditions inside a rocket engine remain difficult to model with perfect accuracy. Ultimate validation would require building and firing actual hardware, accepting failures as learning opportunities, and iterating towards solutions that worked. This situation extended far beyond rocket engines. The Apollo guidance computer, developed at MIT's Instrumentation Laboratory under the direction of Charles Stark Draper, represented the absolute cutting edge of 1960s computing technology. The computer used core rope memory, a form of read-only memory manufactured by hand, with workers physically weaving copper wire through tiny magnetic cores to encode software instructions. Each memory module required weeks of meticulous labor by skilled technicians. The women who performed this weaving, often called the little old ladies by engineers who valued their contributions, developed manual dexterity and pattern recognition skills that existed nowhere else. Those skills vanished completely. The Instrumentation Laboratory's Apollo team dispersed within months of the program's conclusion. The specialized looms and fixtures used for core rope weaving became museum displays. The programming techniques and conventions used to write Apollo software became historical curiosities, studied by computer science students rather than living practices maintained by working engineers. A modern programmer examining Apollo code encounters syntax, structures, and constraints that feel as foreign as ancient Sumerian cuneiform. The guidance computer's erasable memory used magnetic cores as well, arranged in three-dimensional grids that could store data temporarily during flight. Manufacturing these core arrays required precision assembly under microscopic magnification, with failure rates that would be unacceptable in modern electronics production. The Apollo program accepted these failure rates because no alternative existed. Today's engineers would search for different memory technologies rather than recreate obsolete manufacturing processes. But the loss of physical manufacturing capability represents only part of the problem. More devastating in many ways was the evaporation of tacit knowledge, the unwritten, often unspoken understanding that exists only in the minds of experienced practitioners. Tacit knowledge is a concept that sounds abstract until you encounter its absence. It refers to expertise that cannot be easily captured in documents because the people who possess it often cannot articulate what they know. A master machinist who produces perfect parts every time might not be able to explain exactly how they achieve consistent results. Their hands know things their words cannot express. They feel when a cutting tool is beginning to dull before any instrument would detect it. They hear when a machine is operating at optimal conditions versus slightly off. They sense when a setup looks right, even if every measured dimension falls within tolerance. When that master machinist retires, their tacit knowledge vanishes with them. Written procedures capture explicit knowledge, the steps that can be documented and trained. They cannot capture the judgment, intuition, and accumulated experience that transform competent work into excellent work. The Apollo program employed approximately 400,000 people across more than 20,000 contractors and suppliers at its peak. This workforce represented an unprecedented concentration of tacit knowledge within a single industrial ecosystem. Engineers, technicians, managers, inspectors, and production workers developed understanding through years of daily practice, mistake, and correction. They learned which component suppliers could be trusted to deliver consistently, and which required extra incoming inspection. They discovered which written specifications mattered critically, and which represented conservative margins that could be safely adjusted. They developed shortcuts that saved time without compromising quality. They identified potential failure modes before they happened, based on subtle warning signs that no checklist could fully enumerate. All of this knowledge evaporated when the program ended and its workforce dispersed. Workers who had spent years mastering Apollo production techniques moved to automotive plants, aircraft factories, electronics companies, and countless other industries. The concentrated expertise that had existed in the early 1970s diluted throughout the broader economy until it essentially vanished. By 1985, finding someone who had actually worked on Saturn V production required dedicated historical research rather than a simple phone call. Some argue that modern computer-aided design, simulation software, and advanced manufacturing technologies could replace this lost institutional knowledge. We have better tools now, this argument goes. We can model rocket engines in computational fluid dynamics software before building hardware. We can simulate structural loads with finite element analysis. We can manufacture complex geometries with additive printing that would have been impossible using 1960s machine tools. Surely these capabilities more than compensate for whatever institutional knowledge disappeared decades ago. This argument fundamentally misunderstands how complex engineering actually works. Simulation tools are only as accurate as the assumptions programmed into them. Those assumptions require validation against real-world experience. When F1 engineers discovered unexpected combustion instabilities during development, they lacked simulation tools that could predict the problem. But even if such tools had existed, the tools themselves would have required calibration against physical test data. Simulation does not replace testing. It guides testing, reducing the number of tests required but never eliminating the need for physical validation. Modern simulation tools are extraordinarily powerful, capable of analysis that would have required years of hand calculation during the Apollo era, but their power creates its own risks. Engineers who trust simulation results without physical validation can be deceived by modeling assumptions that do not match real-world physics. The history of aerospace is littered with examples of designs that worked perfectly in simulation and failed catastrophically in flight because some physical phenomenon was not captured in the computer model. The tacit knowledge that Apollo engineers possessed included understanding of where simulations could be trusted and where they required skepticism. This meta-knowledge, knowledge about the limits of knowledge, cannot be programmed into software. It develops only through experience, through building hardware and comparing actual performance to predicted performance, through seeing what fails and understanding why. Consider the challenge of rebuilding a Saturn V first-stage fuel tank. The original tanks were manufactured using specialized welding techniques developed specifically for Apollo. The welds had to be perfect because any flaw could cause catastrophic failure during the enormous stresses of launch. Workers who produced these welds spent years developing their skills under intense supervision and inspection. If NASA decided today to manufacture an identical fuel tank, engineers would face immediate obstacles. The specific aluminum alloy used in original tanks, designated 2014-T6, is still produced, but modern production facilities use different processes that might yield subtly different material properties. The friction stir welding equipment used for certain joints has been scrapped. The facilities where workers were trained no longer exist. Even if new equipment could be built and new workers trained, the tacit knowledge of how to produce consistent, flight-quality welds would need to be relearned from scratch, a process that took years during Apollo and would likely take years again. This is not speculation or pessimism. When NASA's Constellation program attempted to develop the Ares 1 rocket in the 2000s, engineers planned to adapt technology from both the Space Shuttle and Apollo programs. Upper stage engines would derive from proven shuttle engines. Solid rocket boosters would scale up shuttle booster technology. Surely this heritage would accelerate development compared to designing entirely new systems. Instead, engineers discovered that adaptation was far harder than new development. Components that appeared simple to modify required extensive redesign when examined closely. Manufacturing specifications that seemed straightforward concealed assumptions valid only within the original context. Supply chains that had provided components for decades had shifted to different products. Qualified workers had retired without training replacements. Each heritage component brought its own archaeology of forgotten knowledge that had to be excavated before progress could occur. The Ares 1 program was eventually cancelled, partly because the cost and time required to resurrect and adapt heritage capabilities exceeded original estimates by substantial margins. What looked like a shortcut on paper became a detour in practice. The institutional knowledge that would have made adaptation straightforward had evaporated too thoroughly to be easily recovered. Perhaps the most disturbing aspect of this industrial collapse is that it happened deliberately, as a matter of conscious policy rather than accidental neglect. Apollo was never designed to create sustainable capability. It was designed to win a race. President Kennedy's 1961 commitment specified landing a man on the moon and returning him safely to Earth before the decade ended. Nothing in that commitment mentioned sustained presence, industrial preservation, or capability for future missions. The goal was achievement, not infrastructure. This goal-oriented framing shaped every aspect of program design. Contractors were hired and facilities built to accomplish a specific series of missions within a specific time frame. Once those missions concluded, the contracts ended and the facilities became surplus. The government had never promised ongoing production. Industry had never planned for it. Everyone understood from the beginning that Apollo was a temporary mobilization rather than a permanent establishment. The funding levels that supported Apollo reinforced this temporary character. The Apollo program consumed a larger share of the federal budget than any peacetime scientific endeavor in American history. This spending level was politically sustainable only because of unique historical circumstances, Soviet competition, national pride, and a public willing to sacrifice for symbolic victory. Once the moon landing proved American technological superiority, the political rationale for such spending evaporated faster than anyone anticipated. NASA's budget began declining in real terms even before Apollo 11 landed. By the time Armstrong spoke his famous words, planning was already underway for program termination. The final 3 planned Apollo missions were cancelled to reduce costs. Production of Saturn V rockets ceased after 15 complete vehicles, even though components for additional vehicles had been manufactured and could have been assembled with continued funding. The decision to terminate production rather than maintain even minimal capability reflected political calculations that prioritized short-term savings over long-term options. Preserving the Saturn V production line would have cost several $1 billion annually in 1970s money. That expenditure would have bought the ability to launch approximately 2 missions per year to the moon, or to deploy massive payloads to Earth orbit. Terminating production saved that money immediately, while foreclosing options that seemed unlikely to be needed. This calculation proved short-sighted, but it was not irrational given contemporary assumptions. Most space planners in 1972 expected that the space shuttle would provide economical access to low Earth orbit, enabling space stations and eventually missions beyond. The shuttle's reusable design was supposed to reduce launch costs dramatically compared to expendable rockets like Saturn V. If the shuttle worked as promised, there would be no need for Saturn V production capability. New vehicles for lunar missions could be developed when the need arose, incorporating lessons from shuttle operations. The shuttle never achieved its promised economics, but that failure only became clear years after Saturn V production capability had vanished. By then, reconstituting that capability would have required investments comparable to the original development. The infrastructure was gone, the workforce had dispersed, the suppliers had moved on, the institutional knowledge had evaporated. This pattern, crash program followed by rapid capability destruction, represents a failure mode that extends beyond space exploration. Large-scale technological capabilities require continuous investment to maintain. The knowledge, skills, and industrial infrastructure needed for complex engineering do not preserve themselves automatically. They must be continuously exercised, or they atrophy and eventually vanish entirely. A society that builds something extraordinary does not automatically retain the ability to build it again. That ability must be actively maintained through ongoing practice, investment, and deliberate knowledge transfer between generations. When those inputs cease, capability degrades, not gradually over decades, but surprisingly quickly. Within 10 years of Apollo's conclusion, rebuilding the program from scratch would have cost more than the original development. Within 20 years, it would have been essentially impossible at any price, because the human knowledge base had dispersed beyond recovery. This is the inheritance burdening modern lunar programs. Engineers cannot simply retrieve Apollo blueprints from archives and begin construction. Those blueprints describe components that cannot be manufactured using existing equipment, from materials that are no longer produced, by workers whose skills no longer exist. The institutional knowledge that transformed blueprints into functioning hardware has evaporated beyond any possibility of reconstitution. Modern programs must therefore reinvent lunar transportation capability from fundamental principles. They can study Apollo's example to understand what challenges will arise. They can learn from Apollo's solutions to avoid repeating mistakes. But they cannot replicate Apollo's methods because the industrial and human infrastructure that made those methods possible exists only in historical records. This reinvention is not necessarily unfortunate. Modern technology offers capabilities that Apollo engineers could never have imagined. Advanced materials, computational tools, manufacturing techniques, and operational experience all provide advantages that could make new lunar vehicles superior to their predecessors in many respects. The spacecraft that eventually returns humans to the moon will incorporate half a century of progress in multiple engineering disciplines. But reinvention takes time that cannot be arbitrarily compressed. Building new industrial capabilities, training new workforces, and developing new institutional knowledge are processes that unfold over years regardless of funding levels or political urgency. Money can accelerate these processes somewhat, but it cannot eliminate the learning that must occur through actual practice. When Artemis program managers describe their timeline for returning humans to the moon, critics often accuse them of excessive caution or bureaucratic bloat. These criticisms miss the fundamental constraint that shapes all schedules. The knowledge base that made Apollo possible no longer exists. Creating a replacement knowledge base requires years of investment, experimentation, testing, and learning. No appropriation can purchase experience that has not yet been acquired. No directive can conjure expertise that must be developed through practice. This is why going back to the moon is harder than going the first time. Modern engineers are not building upon Apollo's foundation. They are building from bare earth, in a landscape where the original foundation was demolished and its materials scattered beyond any hope of reassembly. The blueprints preserved in archives document what was accomplished. They do not and cannot explain how to accomplish it again. The knowledge that sent humans to the moon lived in human minds. Those minds are gone. What remains is the challenge of recreating. in a different era with different constraints, capabilities that a vanished generation achieved through methods we can study but can no longer practice. The Apollo command module contained approximately 2 million individual parts. That number sounds staggering until you realize that the smartphone in your pocket contains roughly the same count of distinct components when you tally every transistor, capacitor, solder joint, and mechanical element. The meaningful difference between these two machines lies not in the quantity of their components, but in the philosophy of their design. Every single part of the Apollo spacecraft existed to accomplish exactly one mission profile: carrying 3 astronauts to lunar orbit, supporting them during their journey, and returning them safely through Earth's atmosphere. Nothing in the command module was reusable for other purposes. Nothing was designed for upgrade. Nothing anticipated missions that had not yet been conceived. This radical simplicity represented Apollo's greatest engineering triumph and explains precisely why its approach cannot be repeated in the modern era. When engineers at North American Aviation received the contract to design and build the Apollo command module in 1961, they faced constraints that contemporary spacecraft designers would find almost liberating in their clarity. The mission parameters were fixed, the crew size was determined, the flight duration was bounded within narrow limits, the destinations were specified. Under these crystalline constraints, optimization became possible in ways that modern programs cannot replicate regardless of budget or talent. Every gram of the command module served a specific documented purpose that engineers could trace directly to mission requirements. Every electrical connection interfaced with other systems through carefully defined pathways that would never need modification. Every structural element was sized for loads that could be precisely calculated because the flight profile was completely known. Engineers could make design decisions that sacrificed future flexibility for present performance because there was no future to consider. The spacecraft was designed to work perfectly for a specific sequence of events, and absolutely nothing else mattered. The hatch design illustrates this philosophy with painful clarity. After the Apollo, one fire killed astronauts Grissom, White, and Chaffee in January 1967. Investigators discovered that the inward opening hatch could not be opened against the internal pressure created by the fire. The redesigned hatch opened outward and could be operated in seconds, but this redesign addressed only the specific failure mode that had caused the tragedy. Engineers did not add redundant hatches, emergency escape systems, or flexible egress options for scenarios beyond the defined mission profile. They solved the immediate problem with the minimum necessary change because the program could not afford delays for comprehensive redesign. This minimum necessary change philosophy permeated Apollo development. When problems arose, engineers fixed those specific problems rather than redesigning systems for broader robustness. The solutions were elegant, efficient, and perfectly adequate for the missions they supported. They were also impossible to extend, adapt, or evolve because extension, adaptation, and evolution had never been design requirements. Modern lunar spacecraft operate under fundamentally different expectations. The Orion capsule, centerpiece of NASA's Artemis architecture, must serve mission types that span a spectrum of durations, destinations, and objectives. The same basic vehicle that carries astronauts to lunar orbit must be capable of supporting missions to the planned Gateway Station in lunar orbit. It must accommodate potential future missions to Mars or its moons. It must dock with vehicles that have not yet been designed, using interfaces that must be standardized before those vehicles exist. It must be manufactured using processes sustainable across decades of production, rather than the few years of Apollo's industrial sprint. Each of these requirements adds complexity that ripples through every aspect of spacecraft design. Consider the life support system as a representative example. Apollo's environmental control system was engineered to keep 3 astronauts alive and functional for approximately 14 days, the maximum duration of a lunar landing mission, including transit time in both directions plus surface operations. The system was simple by necessity, robust through conservative design margins, and completely disposable. When the mission ended, The life support hardware was discarded along with the rest of the command module's interior. Orion's environmental control and life support system must support missions of varying duration with crews of varying size. The baseline system supports 4 astronauts for 21 days, but this baseline represents only one point in an operational envelope that might expand substantially. Missions to the Gateway Station could extend surface expeditions well beyond Apollo's limitations. Eventual Mars transit missions would require life support functioning reliably for years rather than weeks. The same fundamental architecture must scale across this enormous range without complete redesign for each new mission type. Achieving this scalability demands modularity, the ability to add, remove, or substitute components depending on specific mission requirements. Modularity sounds desirable in the abstract. It promises flexibility, adaptability, and efficiency through component reuse. In practice, modularity imposes costs that mount exponentially as systems become more complex. A modular system requires standardized interfaces between components. Each interface must be carefully designed to accommodate all possible combinations of connected elements. The interface specifications must anticipate not only current components, but future components that have not yet been designed. Testing must verify that every potential configuration functions correctly when assembled. Documentation must explain how to integrate, maintain, troubleshoot, and repair systems that might be combined in ways the original designers never specifically imagined. This interface explosion represents one of the fundamental challenges confronting modern spacecraft development. The Apollo command module contained perhaps a few hundred critical interfaces between major systems, connections that required careful specification and verification. A modern modular spacecraft architecture might encompass thousands of such interfaces, each demanding its own design effort, testing protocol, and documentation package. The total engineering labor required to validate a modular design vastly exceeds the effort needed for a purpose-built system like Apollo, even when the modular system performs similar functions. The interface challenge extends beyond physical connections between hardware components. Software interfaces have become equally critical and substantially more treacherous. The Apollo guidance computer executed software, comprising approximately 145,000 lines of assembly code, less than runs a modern dishwasher with digital controls. This code was written by a small, tightly integrated team at MIT who understood every instruction intimately. When anomalies occurred during missions, flight controllers in Houston could trace precisely how the software would respond because the entire code base remained within human cognitive grasp. The flight software for Orion contains millions of lines of code distributed across multiple processors, executing dozens of distinct applications. No single engineer understands the complete system. No individual human mind can hold the full complexity of software interactions that govern spacecraft behavior. Development required hundreds of programmers organized into teams that worked on different subsystems, coordinating through interface control documents and integration testing rather than shared comprehensive understanding. This distributed development model is necessary because no alternative exists for software systems of modern complexity. But distribution introduces failure modes that small integrated teams never confronted. When Boeing's Starliner capsule experienced software anomalies during its first uncrewed orbital flight test in December 2019, the root cause traced to integration failures between software components developed by different teams working to different assumptions. The spacecraft's mission elapsed timer, a fundamental clock that synchronized operations throughout the vehicle, had been initialized using a value from the Atlas V launch vehicle's computer, rather than an independent Starliner time reference. This seemingly minor discrepancy caused the spacecraft to believe it was at a different point in its mission timeline than reality indicated. The vehicle consumed excessive propellant, attempting to execute maneuvers appropriate for a mission phase it had not actually reached. Only intervention by ground controllers prevented complete mission failure. Boeing's programmers were not incompetent. They were wrestling with a challenge that grows inherently more difficult as software systems expand. The number of potential interactions between software components increases exponentially with the number of components. Testing every possible combination of states, inputs, timing relationships, and failure modes becomes mathematically impossible beyond a certain complexity threshold. Engineers must make informed assumptions about which scenarios are probable enough to warrant testing, hoping that improbable scenarios never materialize during actual missions. Apollo's programmers could exhaustively test their software because the total state space was small enough to enumerate and explore. The guidance computer had limited memory, limited processing capability, and limited interface complexity. These limitations, so constraining at the time, actually made comprehensive verification achievable. Engineers could trace every path through the code, identify every possible outcome, and validate that the system would behave correctly under every conceivable circumstance. Modern software complexity has pushed programs irretrievably beyond this threshold. Comprehensive testing is no longer possible in any meaningful sense. Instead, engineers rely on statistical sampling, formal verification methods, simulation, and accumulated operational experience to build confidence that software will perform correctly. These approaches provide reasonable assurance but cannot eliminate uncertainty. Unknown failure modes inevitably lurk in dark corners of code that no test has ever exercised. The hardware complexity of modern spacecraft compounds these software challenges in ways that create multiplicative rather than additive difficulty. Apollo relied on analog systems wherever practical, using mechanical linkages, electrical circuits, and hydraulic actuators that behaved according to well-understood physics. A wire carrying an electrical signal did exactly one thing. It carried that signal from source to destination. Its behavior could be characterized completely using basic circuit analysis. Modern spacecraft replace such analog simplicity with digital systems that require software to interpret signals, process data, and generate commands. A single data bus now carries millions of packets per second, each containing information that must be correctly formatted, routed, decoded, and interpreted. Multiple processors share access to common data resources, raising synchronization challenges that analog systems never presented. Errors in any of these digital processes can cascade through interconnected systems, causing failures that are extremely difficult to diagnose because the evidence vanishes into the digital substrate. This digital transformation has delivered enormous benefits in capability. Modern spacecraft monitor thousands of parameters that Apollo's systems could not even measure. They detect anomalies automatically and respond with pre-programmed corrective actions that would have required ground intervention during 1960s missions. They can be reprogrammed in flight to handle situations their designers never anticipated, adding flexibility that Apollo's hard-coded systems could never provide. But these benefits carry inescapable costs measured in complexity, development time, and verification difficulty. Every additional capability requires additional software. Every additional software module requires integration testing with every other module. Every integration point represents a potential failure mode that must be analyzed, documented, and either eliminated or accepted as residual risk. The Artemis program's Space Launch System rocket demonstrates this complexity trap in concrete terms. The SLS core stage uses RS-25 engines originally developed for the Space Shuttle program. These engines accumulated more than 3,000 successful test firings and flew on 135 shuttle missions over 3 decades. They represent arguably the most thoroughly proven large rocket engines in history, with a performance record that any new engine would require decades to match. Surely, the reasoning went, reusing such mature hardware would simplify SLS development. The engines were well understood. Their manufacturing processes were documented. Their operational characteristics had been validated through millions of seconds of accumulated runtime. Adapting them for a new launch vehicle should have been straightforward engineering rather than research and development. Instead, adaptation proved far more challenging than anyone anticipated. The shuttle's engines were designed to operate in a specific configuration, mounted on the aft end of the orbiter, fed by propellant from the external tank through specific plumbing runs, controlled by the orbiter's flight computers using particular command protocols, subjected to particular acoustic and vibration environments during launch and ascent. The SLS core stage presented a different configuration in almost every respect. The engines mount directly on the rocket's tankage rather than on a separate vehicle. Propellant feed systems follow different paths with different pressure profiles. Flight computers use different architectures, sending commands through different interfaces. The acoustic and vibration environment during launch differs significantly from shuttle's characteristics. Each of these differences required engineering analysis, and many required hardware modifications. More fundamentally, the RS-25 engines destined for SLS needed requalification. An engine qualified for shuttle operations was not automatically qualified for SLS operations, even if the engine itself remained physically identical. Qualification demonstrates that hardware will perform correctly under specific conditions. Change those conditions, and the qualification no longer applies. The engines had to prove themselves in their new context through extensive ground testing before anyone would trust them to carry astronauts. This requalification campaign consumed years and billions of dollars, resources that would not have been required for a purpose-built engine designed specifically for the SLS application from the beginning. The anticipated savings from reusing heritage hardware proved largely illusory. The effort required to adapt, modify, test, and qualify existing engines approached the effort that would have been required to develop new engines tailored precisely to program requirements. The lesson extends far beyond rocket engines. Heritage hardware offers genuine value when it can be used in its original configuration for its original purpose. The moment that configuration or purpose changes, heritage becomes a liability as much as an asset. The documentation assumes context that no longer applies. The qualification data addresses conditions that no longer exist. The institutional knowledge about how to manufacture, test, and operate the hardware may have eroded during years when the systems were not in active production. Apollo avoided this heritage trap entirely by building everything new. The program did not inherit legacy systems from previous efforts that had to be painfully adapted. It did not need to maintain interface compatibility with future systems that existed only as vague concepts. Every component could be optimized for its specific role in the lunar mission, without worrying about whether design decisions would create problems in different contexts years or decades later. Modern programs operate under precisely opposite constraints. Political and budgetary realities demand reusing existing hardware wherever plausible justification can be constructed. Heritage systems come with sunk costs that make continued investment politically easier to defend than starting fresh. Congressional appropriators prefer funding programs that maintain existing contractor workforces over programs that would require building new industrial capabilities. International partnerships impose additional compatibility requirements that further constrain design optimization. The Artemis program involves contributions from the European Space Agency, the Japan Aerospace Exploration Agency, the Canadian Space Agency, and other international partners. Each partner builds components that must interface with American systems according to negotiated specifications. These interfaces cannot be optimized purely for engineering efficiency, because they must also satisfy political requirements about work share, technology transfer, and equitable participation. Long-term sustainability goals add yet another dimension of complexity. Apollo was explicitly a flags and footprints program. Plant the flag, collect the rocks, return home, declare victory. The hardware needed to work perfectly for a few missions and then could be abandoned. Modern lunar ambitions explicitly reject this approach, calling instead for sustainable presence that builds capabilities incrementally over decades. Sustainable presence requires infrastructure that can be maintained, upgraded, and expanded as operational experience accumulates and requirements evolve. Spacecraft must be designed not merely to accomplish their immediate missions, but to support future missions that exist only as notional concepts. Interfaces must anticipate connections to systems that have not yet been designed. Margins must accommodate growth, that cannot be precisely predicted. Every decision made today constrains decisions that will be made years from now. This forward-looking design philosophy is unquestionably wiser than Apollo's sprint-to-the-finish approach, but wisdom carries costs measured in complexity and development time. Designing for the unknown is inherently harder than designing for the known. Testing systems that must work in unanticipated configurations requires more extensive verification than testing systems with fixed, well-defined operational envelopes. The mathematical relationship between complexity and engineering effort is deeply unfavorable. A system with twice as many components does not require merely twice as much effort to develop. The effort scales more nearly with the square of component count, because each component must be verified not only in isolation, but in combination with every other component it might interact with. Double the components, quadruple the integration testing. Triple the components, and testing effort increases by a factor of 9. This exponential scaling explains why modern spacecraft development requires so much more time than Apollo, despite revolutionary advances in computing, materials, science, and manufacturing technology. Better tools do not necessarily mean faster results when the problems being attempted are fundamentally harder. The simplicity that made Apollo achievable within a decade cannot be recreated under modern requirements for flexibility, sustainability, international compatibility, and evolutionary growth. The complexity trap also extends into ground systems that support spacecraft operations. Apollo's Mission Control Center operated using equipment that was state-of-the-art for its era but would be considered museum pieces today. Flight controllers monitored data displayed on paper strip charts and small cathode ray tube screens showing simple numeric readouts and basic graphs. Computers processed telemetry at rates measured in samples per second. Communication links supported voice and limited data transmission. These primitive capabilities enforced simplicity that actually aided operations. When a flight controller saw a parameter trending toward a limit, the situation was usually obvious and the response straightforward. The small number of monitored parameters meant that controllers could develop intimate familiarity with how their systems behaved under various conditions. Experience accumulated through repeated exposure to the same displays showing the same measurements. Modern mission control processes vastly more telemetry from vastly more sensors using vastly more sophisticated software. This enhanced monitoring capability enables better situational awareness during nominal operations and faster diagnosis when anomalies occur. Controllers can see fine details of spacecraft behavior that Apollo-era systems could never reveal. Automation handles routine tasks that once required human attention, freeing controllers to focus on judgment-intensive decisions. But this sophistication creates new failure modes that 1960s operations never confronted. Software crashes can disable monitoring capabilities entirely. Network failures can interrupt data flow between ground systems. Cybersecurity threats require constant vigilance and impose operational constraints that early flight controllers never imagined. Each enhancement that improves capability also adds complexity that demands management. Training flight controllers for modern systems requires substantially more time than Apollo-era training because there is simply more to learn. The systems are more complex, the displays are more sophisticated, the procedures are more extensive, and the potential failure modes are more numerous. Controllers must maintain proficiency across broader technical domains, while also keeping current with software updates that modify system behavior between missions. None of these training costs existed during Apollo because the relevant capabilities did not exist. Modern operations benefit enormously from improved technology, but those benefits come bundled with complexity costs that must be continuously paid throughout program lifecycle. Ground systems that took months to develop for Apollo require years for modern programs. Documentation that filled filing cabinets during the 1960s fills server farms today. This ongoing complexity maintenance represents perhaps the most significant distinction between Apollo era and contemporary spacecraft development. Apollo was a sprint with a defined finish line. Resources were committed, goals were achieved, and then the effort concluded. Modern lunar programs are marathons without clear endpoints. The goal is not merely to land astronauts on the moon, but to establish capabilities that endure and grow over decades. Sustaining capabilities over decades requires continuous investment that Apollo never demanded. Spacecraft designs must be maintained in configuration management systems that track every change and its implications. Manufacturing processes must be preserved even when production rates fall too low to sustain specialized workforce skills. Supply chains must be managed to ensure that critical materials and components remain available despite shifting commercial markets. Institutional knowledge must be deliberately transferred between generations of engineers as experienced practitioners retire and newcomers arrive. The total life cycle cost of a modern spacecraft vastly exceeds its development cost. A vehicle designed to fly for 20 or 30 years requires maintenance, upgrades, and operational support throughout that entire period. Ground systems must remain functional and current. Trained personnel must remain available. Spare parts and replacement components must continue to be manufactured long after initial production ends. Apollo faced none of these sustainment challenges because its vehicles were discarded after single flights, and its program terminated within a decade of serious development beginning. The factories could close immediately after final production because no one expected to need them again. The workforce could disperse because their specialized skills were no longer required. The entire industrial and operational infrastructure could be dismantled because it had served its purpose, and that purpose was complete. Modern programs cannot operate under such assumptions. Sustainability requires maintaining industrial capacity, workforce skills, and institutional knowledge across time spans that exceed individual careers. This continuity requirement represents a complexity burden that Apollo never had to carry, and that adds substantially to the challenge of returning to the moon. The complexity trap is not a symptom of engineering failure or management incompetence. It is an inevitable consequence of attempting sustained exploration rather than one-time achievement. Apollo proved that human beings could travel to the moon and return safely. Modern programs must prove something fundamentally different, that humans can establish lasting presence beyond Earth, building infrastructure that grows and improves over time. The second objective is inherently harder than the first, not because rockets or spacecraft have become more difficult to build, but because sustained presence requires managing complexity that Apollo's purpose-built simplicity deliberately avoided. Every requirement for flexibility adds complexity. Every interface for future expansion adds complexity. Every provision for international partnership adds complexity. Every accommodation for heritage hardware adds complexity. And complexity accumulates not linearly but exponentially, creating development challenges that no amount of funding or technical brilliance can simply wish away. This exponential growth in complexity explains why going back to the moon takes so much longer than going the first time, even with computing power that would have seemed magical to Apollo engineers, materials that did not exist in the 1960s, and manufacturing techniques that border on science fiction by historical standards. The tools are better, but the problem is harder. The destination is the same 239,000 miles away, but the journey has become immeasurably more difficult because we are no longer content merely to visit. We want to stay. And staying requires complexity that visiting never demanded. On the morning of January 28, 1986, ice coated the launch pad at Kennedy Space Center. Temperatures had plunged into the low 20s overnight, far below the design limits for critical components of the Space Shuttle Challenger. Engineers at Morton Thiokol, the contractor responsible for the solid rocket boosters, had spent the previous evening in urgent teleconferences with NASA management, arguing that the rubber O-ring seals between booster segments could not be trusted to function properly in such extreme cold. The seals had never been tested at temperatures below 53 degrees Fahrenheit. Launch morning temperatures hovered around 36 degrees. The engineers recommended delaying the mission until warmer weather arrived. NASA management pushed back. The agency faced schedule pressure from multiple directions. President Reagan planned to mention the mission in his State of the Union address that evening. The Teacher in Space program had generated enormous public interest, with school children across America preparing to watch Krista McAuliffe conduct lessons from orbit. Previous launch delays had already attracted criticism. Another postponement would be embarrassing. Under this pressure, Thiokol management overruled their own engineers and recommended proceeding with launch. 73 seconds after liftoff, hot combustion gases burned through an O-ring seal that cold temperatures had rendered brittle and unresponsive. The resulting flame impinged on the external fuel tank, triggering structural failure. Challenger broke apart at an altitude of 48,000 feet, killing all 7 crew members. The vehicle's crew cabin remained largely intact during the initial breakup, but struck the Atlantic Ocean at over 200 miles per hour after a 2.5-minute fall. No survivable escape system existed. The Rogers Commission investigation that followed delivered findings that transformed American spaceflight permanently. The Commission discovered that O-ring erosion had occurred on previous shuttle flights, with severity correlating to low launch temperatures. Engineers had documented these concerns and communicated them through official channels. Management had classified the O-ring situation as an acceptable risk and continued flying despite mounting evidence of a systematic problem. The very culture that had enabled Apollo's audacious achievements had evolved into something that dismissed inconvenient warnings when they threatened schedules. 17 years later, on February 1st, 2003, the Space Shuttle Columbia disintegrated during atmospheric re-entry, killing another 7 astronauts. The cause traced to damage sustained during launch, when a piece of foam insulation broke free from the external tank and struck the leading edge of Columbia's left wing. This debris strike was observed on launch footage and analysed by a team of engineers who grew increasingly concerned about potential damage to the thermal protection system. These engineers requested that NASA obtain satellite imagery or ground-based telescope observations of Columbia's wing while the shuttle remained in orbit. Such imagery might reveal the extent of damage and inform decisions about whether the crew faced danger during re-entry. Management denied the request, judging that the imagery would not change any decisions and was therefore unnecessary. The vehicle attempted re-entry with a compromised heat shield. Superheated plasma entered the wing structure through the damaged area, progressively destroying the vehicle from within. Columbia broke apart over Texas at an altitude of over 200,000 feet, while traveling at 18 times the speed of sound. The Columbia Accident Investigation Board conducted the most thorough analysis of a spaceflight disaster in history. Their findings echoed the Rogers Commission's conclusions from 17 years earlier with disturbing precision. Engineers had raised safety concerns. Management had dismissed those concerns based on schedule pressure and institutional assumptions about acceptable risk. A culture that normalized anomalies and prioritized operational continuity over rigorous safety analysis had killed another crew. These 2 disasters, separated by nearly 2 decades but connected by common institutional failures, fundamentally transformed NASA's approach to human spaceflight. The organization that once accepted a 4% probability of crew loss during Apollo missions began implementing safety requirements so comprehensive that some observers questioned whether ambitious exploration remained possible. This transformation created what can only be described as a safety paradox. The mechanisms designed to prevent catastrophic failures simultaneously prevent the bold achievements that define meaningful exploration. Understanding this paradox requires examining what Apollo actually accepted in terms of risk. During the 1960s, NASA's internal probabilistic risk assessments estimated that each Apollo mission carried approximately a 96% chance of returning its crew safely to Earth. This figure implied roughly a 4% probability of fatal failure, approximately 1 chance in 25 that any given mission would kill its crew. For the complete program of 11 crewed missions, the cumulative probability of experiencing at least 1 crew loss was mathematically substantial. Apollo engineers and managers understood these odds clearly and chose to proceed regardless. This risk acceptance was not reckless gambling driven by ignorance or machismo. It represented a calculated institutional decision that the strategic importance of reaching the moon justified accepting dangers that would be utterly unthinkable in ordinary engineering contexts. The astronauts themselves were test pilots who had built careers around accepting mortal hazards in exchange for the privilege of pushing boundaries. The nation was locked in existential ideological competition with a nuclear-armed adversary. Failure to reach the moon before the Soviet Union would represent not merely a technical disappointment, but a geopolitical catastrophe, with implications for the balance of global power. Under these extraordinary circumstances, NASA developed an operational culture that prioritized mission success over comprehensive risk elimination. Problems were solved rapidly, often using improvised solutions that had not undergone exhaustive testing. Decisions were made by engineers who possessed deep intuitive understanding of their systems and could assess risks using professional judgment rather than formal probabilistic analysis. Bureaucratic procedures were minimized because they consumed time that the Kennedy deadline could not spare. This culture produced achievements that still inspire awe more than half a century later. When an oxygen tank exploded aboard Apollo 13 halfway between Earth and Moon, flight controllers and astronauts collaborated on improvised solutions using materials at hand, navigating the crippled spacecraft around the Moon and returning the crew safely through a combination of brilliant engineering and extraordinary luck. The mission became legend as NASA's finest hour, a demonstration of what skilled professionals could accomplish when rigid procedures yielded to urgent creative necessity. But this same culture produced near disasters that remained hidden from public awareness for years or decades. Post-mission analysis of Apollo 11 revealed that the lunar module's descent computer became overloaded during the final approach to the landing site, triggering program alarms that nearly caused an abort. Armstrong and Aldrin touched down with fewer than 30 seconds of propellant remaining in their descent tanks, far closer to catastrophe than the celebrating world understood at the time. Apollo 12 was struck by lightning during launch, temporarily disabling multiple spacecraft systems that recovered only through improvised troubleshooting. Apollo 14's lunar module experienced a faulty abort switch that required real-time software workarounds to prevent an uncommanded abort during descent. Each of these incidents could have resulted in crew loss with only slightly different circumstances. The mission succeeded not because risks had been eliminated, but because problems that arose happened to be solvable with the resources and time available. The difference between triumph and tragedy often reduced to factors beyond engineering control: the exact sequence of failures, the specific individuals on console, the particular options remaining when critical decisions had to be made. This reality was accepted as inherent to the nature of exploration. Risk could be reduced through careful engineering and operational discipline, but it could never be eliminated entirely from endeavors that ventured into unknown environments with novel hardware. The goal was to push forward despite danger, not to wait until danger had been completely removed. Complete removal was understood to be impossible. The Challenger disaster destroyed this cultural foundation. The Rogers Commission findings demonstrated that NASA had developed systematic patterns of normalizing problems that should have halted operations. Engineers who raised safety concerns found themselves overruled by managers facing schedule pressures and political expectations. Technical judgments about hardware limitations were subordinated to organizational imperatives about meeting commitments. The institutional culture that had enabled Apollo's calculated risk-taking had evolved into something that dismissed inconvenient warnings as obstacles to be overcome rather than signals to be heeded. The organizational reforms implemented after Challenger fundamentally restructured how NASA approaches decisions involving human life. Independent safety panels were established with formal authority to halt programs that failed to meet defined standards. Risk assessment processes based on quantitative probabilistic methods replaced engineering judgment as the primary basis for flight readiness decisions. Documentation requirements expanded by orders of magnitude, creating paper trails demonstrating compliance with safety protocols at every stage of design, manufacturing, testing, and operations. These reforms addressed genuine failures that had contributed to the Challenger disaster. The investigation had revealed that concerns about O-ring performance existed in documented form, but had not reached decision-makers with sufficient force to override schedule pressures. Creating independent safety organizations with authority to escalate concerns directly to senior leadership provided structural solutions to communication failures that had proven deadly. The independent safety organizations established after Challenger operated with deliberate separation from program management chains of command. Safety officers reported through different organizational pathways than engineering managers, ensuring that concerns could not be suppressed by supervisors facing schedule pressure. Review boards were instituted at multiple program milestones, each requiring formal documentation that identified risks and justified decisions to proceed. Dissenting opinions had to be recorded and addressed rather than simply overruled. These mechanisms created paper trails that would survive scrutiny if disasters occurred, shifting accountability from informal judgment to documented process. But the reforms also introduced constraints that Apollo never confronted and that significantly complicated subsequent programs. Consider the testing and verification requirements that must be satisfied before any modern launch vehicle can carry human passengers. The process begins with component-level qualification, where every individual part must demonstrate performance meeting specifications through testing under conditions that bound the expected flight environment. Components are subjected to vibration levels exceeding flight predictions, temperature extremes beyond operational limits, and operational cycles exceeding expected lifetime usage. Each test generates documentation that must be reviewed, approved, and archived. Qualified components are assembled into subsystems that must then be qualified as integrated units. Interfaces between components are verified through testing that exercises every connection under every anticipated condition. Subsystem testing generates additional documentation layers that reference component qualification records, while adding subsystem-specific verification evidence. Qualified subsystems are integrated into complete systems that require yet another tier of qualification testing. The complete launch vehicle must demonstrate structural integrity under expected flight loads through static testing. Propulsion systems must demonstrate performance through ground firings that replicate flight conditions as closely as ground facilities permit. Avionics must demonstrate proper function through integrated testing that exercises software and hardware together across all mission phases. This qualification pyramid consumes years of effort and billions of dollars before any flight hardware is manufactured. The Space Launch System core stage, despite using propulsion systems derived from space shuttle heritage with decades of operational history, required more than 10 years of development before its first flight. The Orion crew capsule, benefiting from lessons learned across the entire history of American human spaceflight, similarly required more than a decade of development before carrying astronauts. These timelines would have been inconceivable during Apollo, when the Saturn V rocket flew its first crewed mission on only its third launch overall. The previous two flights had carried no crew and served primarily to verify that the vehicle would not explode catastrophically during ascent. By modern standards, this minimal demonstration before trusting human lives to the vehicle appears almost reckless. The complete launch system had been tested only twice before astronauts climbed aboard and rode it toward the moon. Modern safety culture renders such minimal testing institutionally impossible. The accumulated trauma of Challenger and Columbia makes it inconceivable for NASA managers to approve crewed flights without exhaustive demonstration of vehicle reliability through extensive test programs. No individual career can survive a decision to fly that subsequently proves fatal. The professional consequences for managers who approve launches that kill astronauts are total and permanent. The consequences for managers who insist on additional testing before flight are essentially non-existent. This asymmetry of accountability creates overwhelming institutional bias toward caution. The safest career decision is always to require more testing, more analysis, more documentation, more review. No NASA manager has ever been fired for being too careful. Many have seen their careers destroyed for being insufficiently cautious in retrospect. The personal incentive structure makes delay the rational choice regardless of how that delay affects program objectives. The pressure toward caution compounds at every organizational level, creating feedback loops that amplify initial conservatism. Engineers raise concerns because their professional reputations depend on identifying potential problems before those problems cause failures. Managers respond to engineering concerns by requiring additional testing because their careers depend on demonstrating due diligence. Executives require formal risk assessments and independent reviews because their positions depend on defensible decision-making processes. Each organizational layer adds requirements that lower layers must satisfy. Apollo's streamlined decision-making processes would be impossible within this environment. The engineers who made rapid judgment calls during the 1960s would face endless review cycles in contemporary NASA. The managers who accepted significant residual risks would be overruled by oversight boards with authority to halt programs. The executives who pushed development forward despite unresolved uncertainties would find themselves explaining those decisions to congressional investigation committees. The Columbia accident intensified these dynamics substantially. The Columbia Accident Investigation Board report went beyond technical findings to examine organizational culture and decision-making processes in depth that exceeded any previous accident investigation. The board concluded that NASA had failed to learn the fundamental lessons of Challenger, recreating cultural conditions that allowed management pressure to override engineering concerns about known hazards. This finding proved devastating because it suggested that the post-Challenger reforms had been insufficient. The safety organizations established after 1986 had not prevented Columbia. The documentation requirements had not ensured that debris strike concerns reached appropriate decision levels. The risk assessment processes had not accurately characterized the danger posed by foam strikes that had occurred on multiple previous missions. The post-Columbia reforms therefore went further than the post-Challenger changes, adding additional layers of oversight, review, and documentation. Independent technical authorities were established with greater autonomy from program management. Safety review processes were expanded to include more participants and more formal decision gates. The threshold for accepting risks was lowered, requiring more extensive justification for proceeding despite known uncertainties. These reforms were appropriate responses to genuine organizational failures, but their cumulative effect was to make spacecraft development substantially more difficult and time-consuming than it had been even during the post-Challenger period. Programs that had already grown longer, due to 1980s, reforms grew longer, still due to 2000s reforms. Requirements that had already expanded now expanded further. The safety paradox emerges from the interaction between these accumulated requirements and the inherent uncertainties that characterize exploration of unknown environments. Spaceflight involves risks that cannot be completely eliminated through any amount of testing. Novel systems will encounter conditions that no ground test can perfectly replicate. Unknown phenomena exist beyond the boundaries of current knowledge. Residual uncertainty remains regardless of how much effort is invested in risk reduction. Accepting these residual uncertainties is necessary for any meaningful exploration. If programs waited until every conceivable risk had been retired, they would wait forever. Because exploration by definition involves venturing into circumstances where complete knowledge is unavailable. The willingness to proceed despite incomplete information distinguishes exploration from routine operations. But modern NASA has substantially lost the institutional capacity to accept residual uncertainty. This incapacity is not merely psychological or cultural, it is structural, embedded in organizational mechanisms that were deliberately designed to prevent the conditions that led to Challenger and Columbia. Independent safety organizations have formal authority to halt programs that do not satisfy defined criteria. These organizations report outside normal program management chains, making them resistant to schedule pressure. But their independence also means they face no accountability for schedule consequences when they raise concerns. The asymmetry that protects them from management pressure also removes incentives to balance safety against other program objectives. Congressional oversight committees conduct hearings whenever programs experience significant problems or delays. These hearings create documentary records that establish accountability for decisions that may be judged harshly in retrospect. Managers who approve flights must consider how their decisions will appear if something goes wrong. The safest testimony is always that additional analysis was requested, additional testing was conducted, additional reviews were performed. No committee has ever criticized NASA for being excessively careful. Media coverage amplifies any suggestion that safety might be compromised for schedule or budget reasons. Reporters who covered Challenger and Columbia remain alert to similar patterns in current programs. Stories about concerns being overridden or risks being accepted generate attention in ways that stories about methodical progress do not. The external environment systematically punishes perceived risk-taking while ignoring caution. Public opinion, shaped by decades of disaster coverage, expects spaceflight to be essentially safe, despite the extreme environments involved. The loss of 14 astronauts across 2 shuttle accidents created expectations that such losses are unacceptable rather than inherent to dangerous endeavours. Families of lost crew members became advocates for safety improvements, lending moral authority to demands for ever more rigorous requirements. Under these accumulated pressures, accepting the levels of risk that characterized Apollo has become institutionally impossible regardless of how important mission objectives might be. Managers who might personally believe that residual uncertainties are acceptable cannot act on that belief because the organizational systems surrounding them will not permit it. The mechanisms designed to prevent Challenger and Columbia also prevent decisions that accept meaningful risk for meaningful gain. This structural constraint explains why lunar program timelines have extended so dramatically beyond initial projections. Every post-Apollo attempt to return astronauts to the moon has experienced schedule delays measured in years rather than months. Target dates announced with confidence have slipped repeatedly, with each delay attributed to the need for additional verification, additional testing, additional review. These schedule slips do not primarily reflect technical problems, though technical challenges certainly exist. They reflect the accumulated time required to satisfy safety requirements that expand continuously as programs mature and undergo review. Each design review identifies concerns that require additional analysis. Each test campaign reveals anomalies that require investigation and resolution. Each safety assessment generates findings that require corrective action before proceeding. The pace of this verification work cannot be arbitrarily accelerated regardless of funding levels or political urgency. Analysts can only review so many documents per day. Testing facilities can only support so many campaigns per year. Review boards can only meet according to schedules that accommodate participants from multiple organizations. The fundamental tempo of safety verification creates schedule constraints that additional resources cannot easily compress. Some critics observe that commercial space companies appear to operate under different safety constraints than NASA, suggesting that bureaucratic excess, rather than genuine safety requirements, explains NASA's prolonged timelines. SpaceX, in particular, has demonstrated development approaches that would be impossible within NASA's institutional framework. The company's philosophy of rapid iteration, build hardware, test it, accept failures as learning opportunities, rebuild incorporating lessons, has produced remarkable achievements at speeds that make traditional aerospace development look almost paralyzed. There is validity to this observation, but also important limitations. SpaceX's rapid iteration approach functions for uncrewed systems, where failures destroy property rather than kill people. The company has lost multiple rockets during development testing, treating each failure as data that informs subsequent designs. This tolerance for failure during development accelerates learning, but requires accepting destruction of expensive hardware as a routine cost of progress. But when any company begins carrying human passengers, the regulatory environment imposes requirements similar to those governing traditional programs. Human rating demands extensive demonstration regardless of corporate culture. The fundamental dynamic affects any organization that flies humans into space, regardless of ownership structure or corporate culture. Once human lives are at stake, consequences for failure become unacceptable to stakeholders who have legitimate interests in outcomes. Crew families demand accountability when accidents occur. Congressional committees investigate failures that kill astronauts. Insurance underwriters require demonstration of reliability before providing coverage. The broader society expects that organizations entrusted with human lives will exercise commensurate care. These expectations create caution that no institutional reform can entirely eliminate, while also preserving democratic accountability. A space agency that accepted crew losses as routine operational costs would face political consequences that would likely threaten the agency's existence. Public support for exploration cannot be sustained if the public believes that astronauts are being sent to needless deaths. Apollo existed within a brief historical window when this dynamic was substantially suspended. The Cold War competition with the Soviet Union made reaching the moon so important that accepting extraordinary risks became politically viable. Astronauts who died would be honored as heroes who sacrificed for national purpose rather than victims of institutional negligence. The possibility of crew loss was publicly acknowledged and tacitly accepted as the price of victory in the space race. When Apollo 1 killed 3 astronauts during a launch pad test in January 1967, the program paused for 20 months to implement design changes, but never faced serious political threat. The nation remained committed to Kennedy's deadline despite the tragedy. Congress continued appropriating funds. Public support remained strong. The loss was grieved but accepted as inherent to the dangerous endeavor that America had collectively chosen to pursue. No contemporary political environment offers equivalent tolerance. No modern competition creates pressure sufficient to override safety concerns. No current threat makes reaching the moon important enough to justify accepting casualties that better engineering might prevent. The unique circumstances that enabled Apollo's risk tolerance ended when the Soviet Union abandoned its lunar program and the space race concluded with American victory. This means that modern lunar programs must accomplish Apollo-level objectives while satisfying post-Columbia safety requirements. They must explore the unknown while demonstrating that every known risk has been addressed. They must accept residual uncertainty while proving that uncertainty has been minimized to the greatest extent possible. These objectives exist in fundamental tension that cannot be resolved through better engineering or improved management. The safety paradox also creates secondary effects that compound primary timeline impacts. Engineers who spend years preparing documentation and conducting analyses often become frustrated with the pace of visible progress. The most creative technical talent tends to gravitate toward environments where they can build and test hardware rather than produce paperwork. Commercial space companies and other industries recruit aggressively from NASA's workforce, offering opportunities to practice engineering without bureaucratic constraints. This talent drain further slows NASA programs by reducing the experienced workforce available to conduct the verification work that safety requirements demand. New engineers require years to develop the skills and institutional knowledge needed to perform complex technical assessments. Losing experienced personnel faster than they can be replaced creates capability gaps that extend timelines regardless of budgetary resources. Some observers hope that continuing commercial space development will eventually normalize human spaceflight sufficiently to reduce safety requirements. If multiple companies routinely fly paying passengers to orbit, perhaps public expectations will adjust to accept spaceflight as similar to aviation, an inherently risky activity where occasional accidents do not ground entire industries. This hope may prove realistic for routine orbital operations within well-characterized environments. Regular flights by commercial astronauts accumulating operational experience might eventually create comfort levels comparable to early aviation, when crashes were common but air travel nonetheless expanded. But lunar exploration involves hazards beyond routine operations. Each mission ventures into environments that remain genuinely dangerous regardless of accumulated experience. The lunar surface presents thermal, radiation, and terrain challenges that cannot be fully characterized through robotic precursors. The distance from Earth prevents rapid abort to safety in most emergency scenarios. The communication delays complicate real-time support from ground controllers. These inherent hazards will continue affecting lunar programs regardless of how routine Earth orbital spaceflight becomes. The safety paradox will remain operative for ambitious exploration even if it relaxes for commercial activities closer to home. Apollo demonstrated that humans could reach the moon when institutional risk tolerance was high enough to accept significant probability of failure. Modern programs must demonstrate that humans can reach the moon while maintaining risk tolerance that approaches zero. This is the safety paradox stated in its starkest form. We know the destination is achievable because it has been achieved, but the path that succeeded before has been foreclosed by our own accumulated insistence on preventing the failures that path historically accepted. The astronauts who flew Apollo understood they might die. They accepted that possibility because the mission mattered enough to justify personal sacrifice. Modern astronauts accept similar risks, but the institutions that support them are no longer permitted to accept those risks on their behalf. The individual courage remains. The organizational capacity to employ that courage has been institutionally constrained. Challenger and Columbia killed 14 astronauts between them, crew members who perished because warnings were dismissed and schedules were prioritized over safety. These losses created institutional trauma that permanently altered how NASA approaches human spaceflight. The reforms implemented in response addressed genuine failures and have unquestionably prevented subsequent disasters. But those same reforms have also made ambitious exploration vastly more difficult than it was during the era when Apollo demonstrated what determined institutions could achieve. The mechanisms that prevent reckless decisions also prevent bold ones. The procedures that ensure concerns are heard also ensure that programs proceed only at the pace that comprehensive verification permits. This is why going back to the moon is harder than going the first time. The technical challenges, while significant, are ultimately solvable through engineering effort. The safety requirements that now govern human spaceflight may represent constraints that no engineering solution can fully overcome within timelines that maintain political support and institutional patience. The moon remains precisely where Apollo left it, waiting for humanity's return. The distance has not changed. The physics of reaching it has not changed. What has changed, irrevocably, is the institutional context within which that journey must be attempted. We learned too well the cost of dismissing concerns. We built organizations designed to ensure that Challenger and Columbia could never happen again. We succeeded in that goal. And in succeeding, we created a different problem, one that exchanges risk of catastrophe for certainty of delay, trading the possibility of failure for the impossibility of the rapid progress that put bootprints in lunar dust more than half a century ago. The astronauts who walked on the moon did so because their nation was willing to accept that some of them might die in the attempt. Whether any nation will ever again accept such terms remains the open question that defines humanity's future beyond Earth. On the afternoon of May 25, 1961, President John Fitzgerald Kennedy stood before a joint session of Congress and committed the United States of America to achieving a goal of extraordinary ambition. Before the decade ended, he declared, this nation would land a man on the moon and return him safely to Earth. No single space project in this period would be more impressive to mankind, he argued, or more important for the long-range exploration of space, and none would be so difficult or expensive to accomplish. This speech is remembered as a visionary moment when a leader's words bent the arc of history. Textbooks present it as an inspiring call to national greatness, proof that bold presidential rhetoric can mobilize entire societies towards seemingly impossible objectives. What these commemorations typically omit is the political context that made Kennedy's words viable, a context so specific to its historical moment that it can never be recreated regardless of how desperately future leaders might wish to summon similar national commitment. Kennedy's announcement came exactly 43 days after Soviet cosmonaut Yuri Gagarin became the first human being to orbit the Earth. The American response to Gagarin's flight had been a 15-minute suborbital hop by Alan Shepard that barely scraped the edge of space before falling back into the Atlantic Ocean. The contrast was humiliating. Soviet rockets were demonstrably more powerful than American rockets. Soviet space capabilities were visibly more advanced than American capabilities. Soviet propaganda was exploiting this technological superiority to argue that communist systems produced better science, better engineering, and better futures than capitalist democracies could offer. The space race was never primarily about space. It was about proving which system of government and economic organization could better harness human potential. Every Soviet achievement in orbit represented evidence that central planning and collective sacrifice produced results that messy democratic capitalism could not match. Every American failure reinforced narratives about Western decline and communist ascendancy. The competition played out against a backdrop of nuclear terror, with both superpowers possessing weapons capable of ending human civilization within hours. Under these circumstances, Kennedy's moon commitment represented a calculated strategic gamble, rather than an expression of scientific curiosity or exploratory spirit. American rocket technology lagged behind Soviet capabilities for missions in Earth orbit, where the Soviets had accumulated substantial experience and infrastructure. But lunar missions lay far enough in the future that neither nation possessed clear advantage. By redefining the competition around a goal that neither had yet approached, Kennedy hoped to create a race that American industrial capacity could win. This context explains why Congress funded the Apollo program at levels that seem almost hallucinatory by modern standards. At its peak in fiscal year 1966, NASA received appropriations representing approximately 4.4% of the total federal budget. Translated into contemporary terms, this percentage would represent roughly $180 billion annually, more than 7 times NASA's current budget. The agency employed over 34,000 civil servants and funded contractors employing hundreds of thousands more. This funding level did not reflect congressional enthusiasm for space exploration as an inherent good. It reflected terror of Soviet dominance. Representatives and senators who might otherwise oppose massive government expenditure voted for Apollo because losing the space race seemed worse than the budgetary costs of winning it. The Cold War provided political justification that transcended normal appropriations debates about whether taxpayer money could be better spent on domestic priorities. The political consensus supporting Apollo proved remarkably durable across changes in administration and shifting congressional composition. Kennedy's assassination in November 1963 did not derail the program. His successor, Lyndon Johnson, had championed space programs since the 1950s and continued Apollo with even greater personal commitment. When budget pressures mounted during the Vietnam War, Congress trimmed lunar program funding marginally but never threatened its core objectives. Republicans and Democrats, liberals and conservatives, representatives from states with aerospace contractors and those without, all maintained sufficient agreement that reaching the moon before the Soviets mattered enough to justify unprecedented peacetime expenditure. This political environment has no modern equivalent and cannot be recreated through any act of leadership or persuasion. No contemporary geopolitical competition generates comparable urgency. China's space program, while increasingly impressive, does not threaten American security or global standing in ways that motivate emergency mobilization. The Chinese have announced intentions to land astronauts on the moon, but their timeline suggests arrival in the early 2030s, years after American astronauts could return if the Artemis program proceeds successfully. No credible scenario positions China to achieve lunar presence before the United States if America maintains reasonable commitment to its existing programs. Russia's space capabilities have declined substantially since the Soviet era. The nation that launched Gagarin and terrified America into the Apollo program now relies on aging Soyuz spacecraft designs that first flew in the 1960s. Russian announcements about lunar ambitions consistently exceed Russian demonstrated capability to execute those ambitions. The strategic threat that justified Apollo's budget has vanished along with the Soviet state that posed it. Without existential competition driving urgency, lunar programs must compete for funding against every other priority, claiming federal resources. Healthcare expenditures dwarf the entire NASA budget by orders of magnitude. Defense spending exceeds NASA funding by more than 30 to 1. Infrastructure needs, education programs, social services, debt interest payments, all demand resources that might otherwise support space exploration. The case for lunar investment must be argued on grounds of scientific benefit, economic development, technological advancement, and national inspiration, rather than survival against an adversary seeking global dominance. These arguments are valid but insufficient to generate political commitment approaching Apollo levels. Scientific benefits from lunar exploration, while genuine, appeal primarily to specialized communities rather than broad publics. Economic benefits remain speculative and temporally distant, requiring voters to accept current costs for returns their grandchildren might enjoy. Technological spillovers are real, but difficult to attribute specifically to space programs rather than general research investment. National inspiration, though emotionally resonant, provides thin justification when appropriations committees allocate scarce resources among competing demands. The result is funding uncertainty that makes long-term planning extraordinarily difficult for programs requiring decades of sustained investment. The Artemis program's budget has fluctuated significantly across fiscal years, with congressional appropriators providing sometimes more and sometimes less than requested amounts depending on factors largely unrelated to program technical progress. Program managers must constantly adjust schedules and defer capabilities to match available resources rather than optimal engineering sequences. Congressional fragmentation compounds funding instability by preventing stable consensus around program objectives. When Kennedy committed to the moon, there existed broad bipartisan agreement that the goal mattered even if legislators disagreed about details. Members of Congress who questioned specific expenditures nonetheless accepted the fundamental premise that reaching the moon before the Soviets served vital national interests. Modern space policy lacks any comparable agreement. Some legislators advocate for permanent lunar bases as stepping stones toward Mars. Others prefer direct Mars missions that bypass the moon entirely. Still others prioritize scientific exploration using robotic spacecraft that accomplish research objectives without risking human lives. A substantial contingent questions whether human spaceflight deserves priority funding at all when robotic missions achieve scientific returns more efficiently. These disagreements play out through authorization and appropriations, processes that distribute power across multiple committees with overlapping jurisdictions. The Senate Commerce Committee and House Science Committee authorize NASA programs, establishing policy direction and spending ceilings. The Senate and House Appropriations Committees actually provide funding, which may differ substantially from authorization levels. Different committee chairs bring different priorities, different relationships with different contractors, and different visions for what American space policy should accomplish. Navigating this fragmented landscape requires constant attention to political dynamics that shift with elections, retirements, and committee assignments. A program configuration that satisfies key appropriators one year may face hostile questioning the next year after committee membership changes. Contractors located in districts represented by powerful legislators receive protection that contractors elsewhere cannot match. Technical decisions become entangled with political considerations in ways that rarely optimize engineering outcomes. The instability extends beyond Congress to encompass executive branch transitions that historically redirect space policy according to presidential preferences. Each new administration reviews inherited programs and frequently decides to change direction based on different priorities, different advisors, or simple desire to distinguish itself from predecessors. The Constellation program, announced by President George W. Bush in 2004, aimed to return astronauts to the moon by 2020 using newly developed Ares rockets and Orion spacecraft. President Obama cancelled Constellation in 2010, redirecting NASA toward eventual Mars missions while relying on commercial providers for transportation to low Earth orbit. President Trump redirected the agency again in 2017, announcing the Artemis program to return astronauts to the moon by 2024. President Biden continued Artemis but adjusted timelines and priorities according to his administration's preferences. Each redirection imposed costs far exceeding simple administrative adjustments. Constellation cancellation wrote off billions of dollars invested in Ares 1 rocket development. Hardware that had been manufactured was scrapped, Contracts were terminated with penalties. Workforce expertise developed for cancelled systems became irrelevant to successor programs. The institutional knowledge built over years of constellation development partially evaporated as workers moved to other projects or other industries. Artemis itself incorporated hardware originally developed for Constellation, including the Orion spacecraft and elements of the Space Launch System. But this heritage came with complications. Components designed for one program architecture required adaptation for different mission profiles. Contractors who had expected certain funding streams had to renegotiate arrangements. Program management had to maintain continuity despite fundamentally different policy frameworks imposed by different administrations. This pattern of redirection reflects structural features of American government that cannot be reformed away without constitutional changes that no one seriously proposes. Presidents serve 4-year terms and may be replaced by successors with entirely different priorities. Congress reconstitutes every 2 years, with potentially different membership and certainly different political dynamics. No commitment made by one administration binds successor administrations, and no appropriation made by one Congress binds future Congresses. A lunar base cannot be designed, developed, manufactured, tested, launched, and operated within a single presidential term. The infrastructure required for sustained human presence on the Moon requires investments sustained across decades, but American political institutions provide no mechanism for making commitments that span decades. Every program must be rejustified with every new administration and reappropriated with every new Congress. Apollo navigated this challenge through the unique historical circumstances of Cold War competition. The strategic importance of beating the Soviets created continuity that survived transitions from Kennedy to Johnson to Nixon. No president dared cancel the program before achieving the goal Kennedy had established, because cancellation would represent surrender in a competition that transcended partisan politics. No modern lunar program enjoys equivalent protection. Artemis could be cancelled or dramatically restructured by any future administration that decides lunar exploration does not merit continued investment. Commercial providers could be defunded. International partnerships could be abandoned. Nothing in American political structure prevents these outcomes, regardless of how much has already been invested or how close the program might be to achieving its objectives. This political vulnerability affects every aspect of program execution. Contractors must price risk that their contracts might be terminated before completion. Engineers must design systems that can survive funding interruptions that force workforce reductions. Managers must maintain relationships with political stakeholders whose priorities may shift unpredictably. The overhead associated with political uncertainty consumes resources that might otherwise support technical progress. International partnerships add another dimension of complexity that Apollo never confronted in comparable form. The Artemis program includes agreements with the European Space Agency, the Japan Aerospace Exploration Agency, the Canadian Space Agency, the Italian Space Agency, and numerous other international partners contributing various components and capabilities. These partnerships bring resources that NASA could not afford independently, while distributing costs across multiple national space budgets. But partnerships also introduce coordination challenges that can substantially slow progress toward shared objectives. Each partner nation maintains its own political cycles, budget processes, and policy priorities. Components that one partner commits to providing may be delayed when that nation's domestic politics redirect resources. Interface agreements must accommodate different engineering standards, different procurement systems, and different approval processes. Schedule coordination requires aligning activities across time zones, languages, and organizational cultures that approach problems differently. The International Space Station demonstrated both benefits and costs of multilateral space cooperation. The station could not have been constructed without contributions from Russia, Europe, Japan, Canada, and other partners. International participation distributed costs while providing capabilities that no single nation could have afforded independently. The partnership also created political relationships that survived geopolitical tensions and provided frameworks for ongoing cooperation. But the partnership also introduced delays and complications that would not have affected a unilateral program. Russian modules arrived years behind schedule due to that nation's post-Soviet economic difficulties. Interface problems between American and Russian systems required extensive negotiation and engineering workarounds. Decision-making processes that required multinational consensus moved more slowly than unilateral American decisions could have moved. Lunar programs face partnership challenges that exceed International Space Station complexity because the Moon represents strategic territory in ways that orbital platforms do not. Questions about who can conduct what activities in which lunar locations carry implications that low Earth orbit activities do not raise. Lunar resources, water ice, regolith minerals, strategic positioning have potential value that creates incentives for competition alongside cooperation. The Artemis Accords attempt to establish principles governing lunar activities by participating nations. These principles address resource extraction rights, interference avoidance, heritage site preservation, and other issues requiring international coordination. Nations that sign the accords commit to operating according to specified norms that enable cooperative activities while protecting national interests. But the accords' legal status remains contested. They represent political agreements rather than binding international treaties. Not all spacefaring nations have signed. China and Russia notably declined participation, instead announcing intentions to establish their own international lunar research station through bilateral cooperation. The possibility of competing lunar infrastructure operated by different national coalitions creates coordination problems that could affect safety and efficiency for all parties. These geopolitical complications would have been unimaginable during Apollo, when the moon race was explicitly competitive rather than cooperative. American astronauts planted American flags as assertions of American achievement. No international participation was sought or desired. The simplicity of unilateral action enabled rapid progress that multilateral programs cannot replicate, regardless of how desirable cooperation might be in principle. Modern space policy explicitly embraces cooperation rather than competition as the framework for lunar exploration. Official rhetoric emphasizes partnership, commercial participation, and sustainable presence rather than nationalist achievement. These goals arguably represent wiser policy than Apollo's flags and footprints approach, building capabilities that serve long-term human interests rather than short-term symbolic victories. But wisdom and ease are different attributes. The wiser approach is also substantially harder to implement because it requires coordinating multiple nations with different interests, different capabilities, and different domestic political constraints. Every partner that joins a program adds capabilities while also adding complexity. Every interface between national contributions creates potential for delay when any partner experiences difficulties. Commercial participation introduces yet another category of political complexity that early space programs never confronted. The traditional model of space development involved government agencies contracting with private companies to build hardware according to government specifications under government oversight. NASA engineers designed spacecraft in detail, and contractors manufactured those designs, using cost-plus contracts that reimbursed expenses plus negotiated profit margins. This model concentrated expertise within government, while treating contractors as implementers of government decisions. NASA could specify exactly what it wanted, and contractors would build exactly that. Control remained firmly with the agency, which maintained substantial in-house technical capability to evaluate contractor performance and direct design evolution. Modern space policy has shifted dramatically toward commercial partnerships, where private companies develop capabilities using their own resources and approaches, with government serving as customer rather than designer. Commercial crew and commercial cargo programs funded development of SpaceX and Boeing vehicles that those companies designed according to their own engineering philosophies. NASA specified requirements and verified compliance, but did not direct detailed design decisions. This commercial approach offers genuine advantages. Competition between providers creates incentives for innovation and efficiency that cost-plus contracts historically failed to generate. Private investment supplements, government funding, expanding total resources available for space development. Companies that own their systems can market them to other customers, creating revenue streams that reduce government costs for subsequent missions. But commercial partnerships also create political complications. Companies have their own interests, timelines, and constraints that may not align perfectly with government objectives. SpaceX prioritizes development of its Starship vehicle for company reasons that may or may not match NASA's Artemis schedule requirements. Boeing's Starliner program has experienced delays that affected commercial crew timelines regardless of NASA preferences. Managing commercial relationships requires skills different from managing traditional contracts. Government officials must balance encouraging innovation with maintaining safety oversight. They must negotiate arrangements that protect taxpayer interests while allowing commercial flexibility. They must navigate relationships with competing companies that have different capabilities, different corporate cultures, and different lobbying influence. Congressional attitudes toward commercial space remain divided in ways that complicate program planning. Some legislators enthusiastically support commercial partnerships as more efficient alternatives to traditional government contracting. Others view commercial space skeptically, questioning whether taxpayer funds should subsidize private companies that subsequently profit from capabilities developed with public investment. Still, others represent districts with traditional aerospace contractors who fear losing work share to commercial competitors. These competing perspectives produce policy incoherence that affects program execution. Authorization language may support commercial approaches, while appropriations language directs funding toward traditional contractors. Different committees issue conflicting guidance that program managers must somehow reconcile. Political winds shift with elections, potentially reversing commercial policies that programs have incorporated into development strategies. The contrast with Apollo's industrial arrangements could not be more stark. During the 1960s, NASA exercised comprehensive control over every major contractor through detailed oversight that bordered on management direction. Government engineers worked at contractor facilities reviewing decisions and approving changes. Contracts specified requirements with precision that left contractors minimal discretion about implementation approaches. This intensive government involvement reflected both the era's management philosophy and Apollo's extraordinary priority. NASA could attract talent capable of directing contractor work because the agency's mission mattered enough to draw brilliant engineers away from private sector opportunities. The budget supported oversight staffing levels that would be impossible under modern appropriations. The schedule urgency justified government intervention that contractors accepted as the price of participating in the national effort. Modern NASA lacks comparable capacity for intensive contractor oversight. Budget constraints have reduced agency workforce to levels that cannot support Apollo-style involvement in contractor activities. The best engineering talent often finds better compensation and more interesting work at commercial companies than civil service positions offer. Oversight must be accomplished with fewer people possessing less detailed knowledge of contractor systems than their predecessors maintained. This reduced oversight capacity makes commercial partnerships practically necessary rather than merely philosophically preferred. NASA cannot specify and supervise spacecraft design in the detail that Apollo-era practices assumed. The agency must rely on contractor expertise because it no longer possesses sufficient in-house expertise to direct every decision. Commercial partnerships acknowledge this reality while creating frameworks for managing relationships that differ fundamentally from traditional government contracting. The political landscape confronting modern lunar programs thus encompasses multiple interlocking challenges. Funding instability across changes in administration and congressional composition, philosophical disagreements about program objectives and approaches, international partnership coordination requiring alignment across nations with different political systems and priorities, commercial contractor management involving novel relationship structures, and public opinion that supports space exploration abstractly while questioning specific expenditures concretely. Each challenge must be navigated simultaneously while maintaining technical progress toward ambitious objectives that require sustained commitment across decades. Failure to manage any single challenge can derail programs regardless of success managing others. A program that maintains congressional support may still fail if international partners withdraw. A program that coordinates international contributions effectively may still fail if commercial contractors experience difficulties. A program that manages all relationships successfully may still fail if funding is redirected by a new administration with different priorities. Apollo confronted none of these challenges in forms that seriously threatened program execution. Funding was stable because Cold War consensus made lunar exploration a national security priority that transcended normal appropriations debates. Congressional support remained unified because the strategic importance of beating the Soviets overshadowed partisan disagreements about domestic policy. International partnership was unnecessary because American resources alone sufficed for the mission as defined. Commercial contractors existed but operated under government direction through traditional contracts that maintained clear lines of authority and accountability. The political environment that enabled Apollo's success was a unique historical phenomenon produced by circumstances that no longer exist and cannot be deliberately recreated. The Soviet Union collapsed more than 3 decades ago. No comparable adversary has emerged to generate equivalent competitive pressure. The space race that justified Apollo's extraordinary funding and political protection was a singular event in human history, unlikely to recur regardless of how future geopolitics evolves. Modern lunar programs must therefore succeed within normal political constraints that Apollo was uniquely positioned to transcend. They must build and maintain funding coalitions across administrations with different ideological orientations. They must sustain congressional support without the national security arguments that unified Cold War legislators. They must coordinate international partners operating under independent political pressures. They must manage commercial relationships with for-profit entities pursuing their own strategic interests. This is why going back to the moon is harder than going the first time. The technical challenges, while genuine, are ultimately solvable through engineering effort given sufficient time and resources. The political challenges may represent more fundamental obstacles because they reflect structural features of democratic governance that cannot be overcome through technical brilliance or managerial competence. Every president since Kennedy has announced some form of lunar ambition. George H.W. Bush proposed the Space Exploration Initiative in 1989, calling for a return to the moon and eventual human missions to Mars. Congress declined to fund it. George W. Bush announced the vision for space exploration in 2004, directing NASA to develop systems for lunar return. His successor cancelled the resulting Constellation program. Donald Trump announced Artemis with a deadline of 2024. The deadline has slipped repeatedly and will slip further. These repeated failures do not reflect lack of technical capability or absence of national will in any simple sense. They reflect the difficulty of sustaining political commitment across timescales that exceed electoral cycles and administration tenures. Programs that require decades of investment cannot survive in political environments where priorities shift every 4 to 8 years. The patience required for ambitious space exploration exceeds the patience that democratic politics reliably provides. Some observers argue that commercial space development may eventually circumvent governmental political constraints by creating economic incentives that sustain investment independently of political cycles. If lunar resources prove valuable enough to motivate private investment, companies might develop lunar infrastructure regardless of government support. Market forces rather than political consensus would drive progress. This scenario remains speculative. No demonstrated lunar resource has yet proven valuable enough to justify commercial development costs at scales sufficient for human presence. Water ice at lunar poles might eventually support economically viable operations, but the infrastructure required to extract and utilize lunar water requires initial investments that no private entity has shown willingness to make. Government funding remains essential for the foreseeable future, meaning government political dynamics will continue determining program viability. The question facing humanity is not whether returning to the moon is technically achievable. Apollo answered that question more than half a century ago, when 12 astronauts walked on the lunar surface and returned safely to Earth. The question is whether modern political systems can generate and sustain commitment necessary to repeat and extend that achievement under conditions fundamentally different from those that enabled the original success. The moon waits 239,000 miles away, unchanged since Apollo astronauts left their bootprints in its ancient soil. The American flags they planted have likely bleached white under decades of unfiltered ultraviolet radiation. The descent stages of their lunar modules stand as monuments to what unified national purpose once accomplished. The technological artifacts they left behind, retroreflectors, seismometers, sample containers, remain where they were placed, awaiting visits by successors who have not yet arrived. Getting back to those monuments requires navigating a political maze that Apollo never had to enter. The shortcuts that enabled Apollo's success, unlimited funding, unified political support, freedom from international coordination requirements, complete government control over contractors, have been permanently closed by changes in the geopolitical environment and evolution in how democratic societies make decisions about large-scale technological investments. The political environment that put humans on the moon was a product of unique historical circumstances: superpower competition, nuclear terror, ideological struggle for global allegiance. Those circumstances created willingness to spend and willingness to risk that normal politics would never generate. When those circumstances ended, so did the political conditions that made Apollo possible. Modern lunar programs must find different paths through a different political landscape. They must build coalitions that survive changes in administration. They must maintain congressional support without Cold War urgency. They must coordinate partners with independent agendas. They must manage commercial relationships without losing sight of public objectives. Whether these challenges can be overcome remains uncertain. The history of post-Apollo lunar ambitions provides little cause for optimism. Program after program has been announced, funded partially, and then cancelled or restructured before achieving its objectives. The pattern suggests that perhaps democratic political systems cannot sustain the patience required for endeavours that span decades. Or, perhaps Artemis will prove different. Perhaps the combination of commercial partnerships, international cooperation, and incremental progress will create momentum that survives political transitions. Perhaps accumulated investment will eventually reach levels where cancellation becomes more costly than continuation. Perhaps human presence on the moon will finally be established despite the political obstacles that have frustrated every previous attempt. The outcome remains unwritten. What is certain is that the political dimension of lunar exploration has become at least as challenging as the engineering dimension. Solving the technical problems means nothing if political support evaporates before solutions can be implemented. Building the hardware accomplishes nothing if funding is cancelled before missions can fly. This is the final reason why going back to the moon is harder than going the first time. The physics has not changed. The engineering is well understood. But the political environment that enabled the original achievement has vanished completely, replaced by a landscape of fragmented authority, competing priorities, and institutional constraints that no amount of technical excellence can overcome by itself. Apollo succeeded because extraordinary circumstances created extraordinary political conditions. Modern programs must succeed despite ordinary conditions, or not succeed at all.